In this video, I will be starting with the complex function, right, to understand the foundation of analytic functions and its properties, right. And as you know that what is the complex number, that is the complex set of complex numbers denoted by capital C is a subset, a superset of a set of real numbers, right, and it is the biggest set ever known. And what is the function? You know that in real analysis, what is the real function? It is generally denoted by y is equal to fx, a real function, where x is called input and y is called the output, right? And obviously, if a function small f is defined from a set capital A to set capital B, obviously both are the subsets of real numbers. Then you may write it like, in real analysis, real function, consider y is equal to fx, a real function, right, from set A to set B, and they both are subsets of real numbers, right. You call this x as an element of domain. Domain capital A is called domain, capital B is called codomain, right, the input output structure. And the values taken by small f, that is fx, that is called the range of function, right, and that has to be the subset of this capital B, right. Okay, then this is called a real function, and obviously you can take any example, y is equal to x square, y is equal to x plus 1, anything, right. But here we want to deal with complex functions, right. Similar to this, as we see that x is the real input and y is the real output, right. If I allow me that this becomes a complex input and the output is also complex, then we call it a complex function, right. And then we can define a complex function by saying that a function having the domain and codomain as the subsets of complex numbers is called a complex function, right. And a complex function can be denoted by, just similar to this, y is equal to fx. A complex function is denoted by this w equal to fz, right, where z is the input, a complex number, and w is an output. Obviously that will be a complex number, right. So this is the representation we will be going to use for a complex function, right. So consider y is equal to fx from set A to B, that is a real function, and this is what we are going to deal with, complex function, right. Similarly, w is equal to fz is a complex function from set S to S dash, and capital S is a subset of set of complex numbers, and S dash is also a subset of complex numbers. Means the input set and the output set both are set of complex numbers or subsets of complex numbers, right. And w is equal to fz is a notation, right. For example, w is equal to z square, right, or you may write it as w is equal to fz is equal to z square, w equal to fz equal to z square. This is an example of complex function, right. And you know that z is a complex number, right, and z is equal to x plus eta y. A complex number can be written as x plus eta y whole square, right, and then you can square it. On squaring you will be getting x square minus y square, because eta square equal to minus 1, and then the imaginary parts eta times 2xy, right. And you can see that your function, complex function, or sometimes you call it complex valued function, right. So generally we skip the word complex valued, we call just complex function, means complex valued function, right. So this complex function actually consists of the two real functions. This is, you can see that this is a real function of two variables x and y, and this is also a real function of x and y, right. So it can be written as a function u of x and y, and eta times v as a function of x and y, right. This is w. or W equal to Z. Right. So from here you can see that a complex function can be expressed as the sum of, not just a direct sum, you have to put an eta before the second function, linear sum, you can say linear sum with the constants 1 and eta, right, and that is called the basis, right. So linear sum of two real functions, spatial linear sum together with this eta here, right. So we can study a complex function as in the terms of real functions also, but that real function should be from R2 to R2. If you focus on it, you can see that this is the coordinate x comma y, right. So this part, this real function takes the input from R2. R2 means xy plane, right. You write it this way, R2, right. And this is also a function which takes the input from R2, means both the real and imaginary parts of our complex functions takes the input from the set R2 x y plane, right. And then the original functions, means the sum function, complex function, has the output in R2. You can see that this will be a real number and this will be a real number, and obviously that will be of the form u plus eta v. Again, that can be represented on R2 plane, right. So a complex function may be viewed or may be equivalent to a function from R2 to R2, right. And now I will go to again back to this my real function, right. The problem is that, however, it is clear that a complex function, what is a complex function, but the problem is we cannot draw the graph of a complex function, and that's why it is very hard to imagine about the complex function or the graph of complex function, right. If you see this y is equal to fx, take any a real example or real function example. If I take, consider again a real function, let me take y is equal to fx is equal to, suppose I take x plus 1, right, and you can see that you can input any x, means x is defined for all real values of x, and this is the output x plus 1. If I try to draw the graph will be like this. This is the y-axis or fx, and this is the x-axis, and if you input plotting the graph for this right hand side part for positive values of x, if I input 0 here, then I will be getting 1, means this will be 1, 0, 1, right, and then increasing my x, the value of y will increase linearly, and the graph will be like that, like this, right, means this is the y-intercept, this is 1, this is called c, y is equal to mx plus c, and this line has slope equal to 1, there is the angle of 45 degree with the horizontal line, right. So this is the graph for y is equal to fx, and this is not the case with this complex function, right. You cannot draw the graph of a complex function as you are able to draw the graph in case of a real function, right. So in order to visualize how the graph of a complex function looks like, I will give a small manipulation for this graph. If you look this graph closely, you can see that if you input x equal to 0, you will get f0 equal to 1, right. For input 0, you get 1. If you input here 1, you will get 2. For input 3, you will get 4, right. So if I draw these two lines, x-axis and y-axis, not perpendicular to each other, these are drawn perpendicular to each other, rather drawing them perpendicularly, if you draw them parallelly, right, if you place this y-axis parallel to this x-axis, right, and then plot these points, then what will happen, right. Okay, so, or I can draw it a new way, x-axis, and then placing this y-axis not vertically, rather I should place it horizontally, right, or parallel to this x-axis, right, and this is my 0, x equal to 0, and this is my 1, this is 2, and so on, right. So when I input x equal to 0 here, I will be getting y equal to 1, right. So for x equal to 0, y will be 1, 1. For x equal to 1, y equal to 2, right? 2, and so on, right? So the graph will look like this. If I draw the graph, then the image will be like this, right? You can see that the image of this function starts from 1, right, corresponding to this x equal to 0. This is your domain, right, and this is your image, and you can see that every point of the x-axis gets shifted to the right by 1 unit. Means 0 gets shifted to the right by 1 unit, 1 gets shifted to 2, and so on for all the intermediate points, right? So this is the idea behind the drawing of a complex function, right? This will be our basic idea, right? In spite of taking the axis perpendicular to each other or taking on them only on one plane, I have taken two different copies of axis. One is x-axis and parallel y-axis, right? And you can see that every point gets displaced by 1 unit. So this is your domain and this is your range, right? And obviously this is your codomain. Fine. This is your range, right? Okay. Now I will take a complex function similar to this, right? And will try to draw it. But before drawing that, you can see that this is a linear equation, right? And here the function is a real function, obviously. And since to plot a real function, we need a board. This board is a two-dimensional plane. Fine. So to draw a real function, we need a board or a two-dimensional plane, right? We need 2 dimensions in order to draw real function. Similarly, in order to draw a complex function, we will be needing 4 planes or 4-dimensional space, right? Because the input z is of 2 dimension, x plus eta y, right? And the output is also of 2 dimensions. So we will be we should have 4-dimensional space in order to draw this complex function, and that is not practically possible, right? So what we'll do, we will draw our complex function just similar to this, right? We'll take 2 planes, one plane z plane and image plane will be w plane. Z plane will be a domain plane and w will be our codomain plane, right? So rather taking 4-dimensional space, and because that is not feasible, I will take 2 parallel copies of planes, right? You can imagine that you are sitting in a room, the opposite walls of your room will be like 2 copies of complex plane. Suppose you are sitting in a 4-sided 4-walled room. The left hand side wall of your room should be the z plane, right? And the right hand side wall of your room should be the w plane, right? So that can be thought of a complex function, right? Okay. So, okay. Before that, I have to okay. I will draw those 2 planes. One is the z plane and w plane. Let this be your z plane, and this is infinite, right? Z plane. This is an infinite plane, right? And parallel to this, you draw w plane. W plane, right? So here in this plane, z plane, you will have your domain that is denoted by capital S. Suppose this is a domain, okay, domain set S, right? And on w plane, you will be having its image, and let me denote it by S dash. Suppose this is the image, right? Something big, magnified, okay, S dash, right? Okay. And between them, there is a complex function which is working like a machine, right? Taking the input from this and giving the output as dash. Fine. So this is the idea. right, to represent a complex mapping, right? This whole two planes, one plane, second plane, right? Okay. And yes, before actually drawing a graph of a complex plane, let me take a simplest example. We have an equation of line is the simplest example in real analysis or draw real function. I will take the simplest examples y is equal, w is equal to z, or w is equal to alpha z plus beta, kind of this, right? So first I will be taking to understand the concept of this complex mapping graph. Let me take the first mapping as a translation mapping, the simplest, right? W is equal to z plus b, right? The first will be translation. Okay, it is defined as, let me denote it by symbol capital T, and you know that the input is z, right? And z plus b, where b is complex number, right? And let me denote this by let's see, complex number, or c, right? This b is a complex number, z is the input, and the output is tz, right? T stands for translation, right? Then what does this mapping actually do? This mapping, tz, translation mapping, translates each point z naught, let me take it z naught, of the domain set S, right, to the point tz naught of the codomain set S dash, right? Means every point of the domain S gets translated by the same amount, and that amount is equal to the vector b, right? B is a complex number, so I can call it a vector, right? Yeah, that's why we are calling it translation, because every point of the domain gets translated by the same amount, and that amount is actually equal to b, right? Amount means by magnitude of b and by the direction of b, because b is a complex number, right? And let me take a small example of this. B, okay, fine. Then every point z naught, right, is transformed to t z naught of every point z naught, every point z naught belonging to domain S gets tz naught belonging to image set S dash, right, translated or shifted by vector b, right? And yes, so this is called translation, right? And let me take a small example. Suppose let me take, for example, if I take t z equal to z plus 1 plus iota. You can see that z plus 1 plus iota, this 1 plus iota is actually b, complex number, right? Okay, and take S. S is a triangle, right? And S is a triangle with z with vertices z equal to 0, z equal to 1, and z equal to iota, right? So we have to find the image of triangle, and the triangle is placed on z plane, and the image will be obtained on w plane, right? So I'm going to draw the z plane first, right? The domain set. So this is my z plane, and z plane consists of x and y axis, right? I'm writing here z plane, right? And let me draw these points z equal to 0, 1, and iota. Z equal to 0 is this point, let me call it A. Z equal to 1 is this point, let me call it B. And this is C. So this is the domain set S, right? Fine. You can write z equal to 0 here, z equal to 0, and this is z equal to 1, and this is z equal to eta, right? Now, putting z equal to 0 here will give, you see that t0 will give you 1 plus eta, right? t1 will give you 2 plus eta, and t eta will give you, I think, 1 plus 2 eta. Fine, right? So I have put these 3 points here in my mapping, and these are my outputs. Now I will be going to draw these, to plot these points on my image plane, that will be my W plane, and this is my W plane consisting of u and v axis, right? And you can see that the function can be written as u plus eta v. So the u axis and the v axis, right? This is u axis and this is v axis, right? So corresponding to z equal to 0, the point is 1 plus eta. If you draw 1 plus eta, it will be that 1, 1. This is 1 and plus eta here, right? It will be here. V axis, u axis, right? 1 and 1 and 2, right? 1 plus eta, this point. So this is your a dash. Similarly, 2 plus eta, so that point will be here, b dash, and then 1 plus 2 eta, 1 plus 2 eta, here, 2 eta. This is your point C, right? C dash, sorry, and then you join them. Fine. So this is your image S dash, right? And you can see that your whole triangle gets translated by the amount 1 plus eta. If you watch it closely, every point you can see those A, B, and C point. You can see this point Z equal to 0. Z equal to 0 gets shifted by 1 plus eta, means 1 in the direction of x-axis and eta in the direction of v-axis, u-axis and v-axis. Sorry. And your point Z equal to 1, that was actually here, that is also shifted by factor 1 plus eta, means 1 along u-axis and then 1 along v-axis, right? And this is Z equal to 1 plus 2 eta, right? Fine. So this is what we call as translation, right? Now I will be taking another simplest complex mapping, and that is rotation, right? Rotation. Fine. And rotation is defined as, let me call it R, rotation. RZ equal to AZ, right? And where A is a complex number, right? Fine, A is a complex number. Then the domain set S dash, right? Or you can say that every point of domain set S dash every point Z naught belonging to S, right? gets rotated by the angle equal to argument of this A, right? This complex coefficient of Z, to give T Z naught belonging to S dash, right? So the rotation actually rotates the whole domain, right? If I take this example again, this triangle will be rotated, right? Not translated, rotated by this angle, argument of A, and that rotation can be clockwise or anti-clockwise depending on the sign of this argument A. If argument A is positive, if argument of A is positive, then the rotation is clockwise, anti-clockwise rotation, sorry, anti-clockwise rotation. And if it is negative, then it will be clockwise rotation, right? And vice versa. Fine. So taking that example again, my domain set S will be same. For example, consider R Z equal to, let me take any complex number, and let me take it 1 by root 2 plus eta by root 2, fine, Z, right? You can see that this is a complex number, fine. And yes, S is same. S is a triangle with vertices Z equal to 0, Z equal to 1, and Z equal to eta, fine. Then this is my y-axis, x-axis, this is my z plane, and I will draw my domain set S, that is actually the vertices of triangle A, Z equal to 0, and B, here we have Z equal to 1, and it is C, Z equal to eta. Then this is my triangle S, right? And now applying this rotation mapping, putting Z equal to 0 here, I will be getting R0 equal to 0, you can see that. Then R1 equal to 1 by root 2 plus eta by root 2, and then R third point eta, that will be minus 1 by root 2 plus eta by root 2, fine. And then drawing my W plane on the same scale, right? V, U, and this is my W plane, fine. And plotting this point 0, this A dash, Z equal to 0, and then another point B dash 1 by root 2 plus eta by root 2, and this point will be something like here 1 by root 2, 1, this is 1, same on same scale. If this is 1, then it should be 1, right? Then 1 by root 2, right? 1 by 1.4, right? That will be less than 1, obviously. So something like here 1 by root 2 plus eta by root 2, here, suppose it is here. B dash Z equal to 1 by root 2 plus eta by root 2, and another point minus 1 by root 2, it will be here C dash Z equal to minus 1 by root 2 plus eta by root 2, and then completing the picture, this will be your range set S dash, and you can see that the whole triangle gets rotated anti-clockwise, right? Anti-clockwise by an angle of 45 degree. If you see this 45 degree angle, right? And obviously that 45 pi by 4, it comes from this. If you find the argument of this thing, where is that? Argument of this ARG, argument means angle for this complex number 1 by 2 plus eta by root 2, and that is equal to tan inverse 1, right? Because argument of a complex number is defined, suppose this is x plus iota y, then the argument is given by tan inverse y over x, and see that y is 1 by root 2 and x is 1 by root 2. So on cancellation it will give me tan inverse 1, and that is eventually equal to pi by 4, and that's why the whole triangle gets rotated by the angle pi by 4 anti-clockwise, right? So this is the idea behind rotation, right? And now I will be taking the third, is called magnification. Fine. Magnification. And magnification is defined as the same way. mz, I will write mz equal to az, right? It is defined as mz equal to, let me write it as az, right? And one more thing, here if you want only rotation, not magnification, then the modulus of this thing should be 1. Let me write it here. And modulus of A should be equal to 1, right? Means if you want the pure rotation, right? And it is defined as this, okay? A belong to real number, fine, right? It should be a real number. If you allow your A to be a complex number, then that will give me rotation too. Means that will be a combined case of magnification as well as rotation. I am discussing here the pure case of magnification, no rotation, right? That's why I have avoided it as a complex number. I should take it as a real number, because had it been a complex number, then there will be certainly some argument, and after getting this argument, the figure will be rotated by that angle, right? So I don't want rotation. That's why I have taken this as a real number. If you take this as complex number, that is also fine, but that will be a mixed case of magnification as well as rotation, right? So A is a real number, right? Then in that case, then domain S gets magnified by the magnitude of this by amount mod of A, right? Fine. And magnification is also possible, contraction is also possible, shrinking is also possible if this A is less than 1, magnified by the amount this. If A is greater than 1, then magnification, or you call it expansion, right? Expansion, okay. And if this A is lesser than 1, then there is a contraction, shrinking, contraction, right? Or I should write it as mod A. Fine. Mod A is greater than 1, mod A is less than 1, then contraction, right? And contraction is a negative magnification. That's why the case is magnification. Fine. Then taking the same example, I can take it right here. Okay. Same example. Mz equal to 2 times of z. I have taken this A as a real number, and my domain set S is same, a triangle with vertices z equal to 0, z equal to 1, and z equal to iota, right? And you can see that the S is same, this triangle, right? So let me draw the image set only, because the domain set is already drawn. I am not drawing that again. So corresponding to this, I should rub it. Okay, now see, this is my domain set, right? This is already drawn. Then I will write here the values of M. See, M, the first input 0, that will give me 0, right? Is that m 2 times 0 0. Then m1 will give me 2, right? 2 times of 1. And third is m eta will give me twice of eta, right? And then plotting these points, plotting these points, I will get, this is my v axis and this is u axis. The first is 0, this is 0, a dash z equal to 0. Then 2 will be here, 1 and 1 2, b dash z equal to 2, right? Then c dash 2 eta, c dash z equal to 2 eta, and then drawing it s dash, and this is my w plane, and you can see that the original triangle S gets magnified by a factor of 2. And how do I know that it is magnified by a factor of 2? Due to the presence of this A, and if you find mod of A, mod of 2, that will be 2, means the image will be twice of the domain, right? So these are the simplest mappings to understand the drawing of a complex function. Our focus is to draw a complex function, to draw the graph of a complex function, and in order to draw the graph of a complex function, you need 2 copies of complex plane, right? One is z plane and another is w plane, right? And in real life, the example of this complex mapping is a projector, right? In every classroom there is a projector, and that has this display on the board in front of you. This is a kind of complex mapping, right, where the input is given to the projector and then the image is obtained on the whiteboard, right? So your projector is like a machine, is like a complex function, and that is taking input from a text file or image file, that is called your S, domain S, right? The input, the source input of your projector is the domain S, and the output that is displayed on the board, that is your S dash, right? And you see that sometimes the text gets magnified, or you can use your projector to magnify the image, or you can use your projector to translate the image also, right? And you can rotate that image also. So you can see that rotation, magnification, and translation are all the components of a projector that you use in a classroom, right? So that's a good example to understand a complex function. And another example is that if you try to draw a figure of a circle, right? If I say you to draw a circle, then immediately the figure of the circle will pop up in your mind, and that is the z plane, and then immediately you try to draw it on paper, and maybe you can draw the same as you have thought. The drawing on the plane is your w plane. Whatever you thought, that was your z plane, on your z plane, and whatever you have got after drawing, actual drawing, there is a w plane, right? Means your imagination plane is z planes, and the actual you are plotting on its paper, there is a w plane, right? And there is a slight difference, always a slight difference. Who is not a painter, always a slight difference. What is your imagination and what is your drawing? There is a slight difference, and that is a good example, right, of this complex mapping. Fine. In the next video, we will be taking the combination of these 3: rotation, magnification, and this translation, and that's called a linear mapping. Most general of these 3, that will be a type of nature. This AZ taken from these 2, and this plus B, that will be kind of AZ plus B mapping, that is called linear mapping. We'll be discussing that in our next video. For this video, thank you.